Good morning, everybody. I hope you are well. Today we will continue with capacitance and dielectrics. Very important lecture, especially for technological applications. Capacitors are used everywhere in the industry, in the integrated circuits, also dielectrics. And we will talk about the relation between capacitors and dielectrics. What we have listened the chapter. First of all, we will discuss the nature of capacitor, what is the capacitor, and how to measure, how to calculate the capacitance of capacitors. In addition to that, we will learn how to calculate a quantity that measures their ability to store charge. Capacitors store charge. During the first lecture, we have learned charge, okay? And within the capacitors, we can store charge. So we will learn this one. And we will analyze capacitors connected in a network, seriously connected or parallel connected capacitors. And we will calculate equivalent capacitance of the capacitors connected in series or parallel. In addition to that, we can store energy into the capacitors, and today we will learn how to calculate the amount of energy stored in a capacitor. And in the next lecture, we will talk about dielectrics. So what dielectrics are and how they make capacitors more effective. We will discuss this one. And finally, we will learn how to use Gauss laws when dielectrics are present. Actually, let me tell you here something. Capacitors are related to the electric potential, which we have learned during the last lecture. And if you know the electric potential, then you can better understand the capacitors. Okay, especially when you are dealing with the problems of this chapter, your previous information on electric potential will be very helpful. Don't forget this one. Here, let me discuss the advantages of the capacitors, where they are used. Actually, we use them in our daily life. In flash photography, for example, here you see mobile phones. The energy used to make the flash is stored in a capacitor, which consists of two closed space conductors that carry opposite charges. And the energy of a capacitor is actually stored in the electric field. So we will discuss all these things, energy storage in capacitors and how to release this energy and how to store this energy and what is the relation between energy and electric field stored in capacitors. Let me start with two conductors. On the right side, here you see a positively charged conductor, conductor A, and it has positive Q charge. And here with the blue color, we have conductor B, it is negatively charged. And they are separated from each other by an insulator or a vacuum. Okay, let's consider in this case there is a vacuum here between the conductors, and this forms a capacitor. When we charge the capacitor, it means that two conductors have charges with equal magnitude and opposite sign. Just consider that this is a capacitor on the right side, and you charge this side with this positive Q, and you should have same amount of charge on the negative side, okay? And what about the total charge on the capacitor? The net charge on the capacitor is 0. This is the definition of capacitor. And how to store charges on a capacitor. Let me draw it here. Let's consider here we have one plate. Here we have another plate, and there is a certain distance in between. And these plates are connected to a battery here. This is the battery. And one pole of the battery, another pole of the battery. And these plates are connected to the terminals of the battery. So by using this battery, we can charge the capacitor, okay? And then the potential difference between the plates of the capacitor, between the conductors of the capacitor, VAB, is equal to the voltage provided by this battery, okay? So we have capacitor, we have two plates, and we would like to charge this capacitor, and then we use battery. We connect these wires to the terminals of the battery, and then we store charges on the capacitor. So finally, we will have a potential difference between the plates, okay? And this potential difference is given with the voltage of the battery, okay? If we change the magnitude of charge on each conductor, here, let's say we have conductor 1, and here we have conductor 2 of the capacitor. And if we change the magnitude of charge on each conductor, the potential difference between conductors changes. So we are talking about same capacitors, okay? So here we have a capacitor and it has certain two plates. And here we have the same capacitor with the same plates, okay? And we store charges on this plate and charges on this plate. So after a certain time, you continue to increase the charges on the plates. Now we have positive 2Q and negative 2Q on the same capacitor. And if we change the magnitude of charge on each conductor, the potential difference between conductors changes. So here at the beginning, the potential difference is AB1, let's say, and now we have VAB2. So potential difference changes with the change in the magnitude of charges on each conductor. But what about the ratio of charge to potential difference? The charge potential difference ratio. This ratio does not change, and this ratio is equal to capacitance of a capacitor. I hope it is clear. This is the capacitance of a capacitor. This is the magnitude of charge on each conductor. Don't forget, it is not the total charge. It is just magnitude of charge on each conductor. Okay, here we have conductors of the capacitor. And let's say this is charge with positive Q and this is charge with negative Q. And this Q is the magnitude of charge on each conductor. And here we have VAB, potential difference between conductors. Okay, and this is the capacitance of a capacitor. So don't forget this formula. Please always keep this information in your mind. It will be very helpful. Do you have any question here in this part? Then let me continue with the parallel plate capacitor. Actually, you can understand from the name, a parallel plate capacitor consists of two parallel conducting plates separated by a distance, and this distance is very small compared to their dimensions. Here we have upper plate, it is charged with positive Q, and it has certain area A. And here we have another plate, bottom plate, it is negatively charged with negative Q, and this is the distance between the plates. And this distance is small compared to their dimensions. Okay, and this is the potential difference between the parallel plates. This is the parallel plate capacitor, and the mechanism is same, and the capacitance of this capacitor is given with Q over VAB. Okay, this is the capacitance of capacitor. We can also write the capacitance of a parallel plate capacitor in vacuum with this form. You know this one, Q over VAB. On the right side we have epsilon 0, and here we have area of each plate, and here we have D, distance between plates. So capacitance of parallel plate capacitors can also be written A over D, right? A is the area of the plates, and D is the distance between the plates. So without knowing the charge information or potential difference information, you can also calculate the capacitance of capacitors by using its dimension informations. Okay, don't forget this one. And look at this equation. Here we have epsilon 0. This is electric constant we have learned during the previous lectures. So it is constant. So then here we have area and distance between plates. So they give us the capacitance of a capacitor. So if I change the design of the capacitor, then I can manipulate the capacitance of the capacitor. So then look at this statement. The capacitance depends on only the geometry of the capacitor. Why? Because it depends on the area of each plate, because it depends on the distance between the plates. Now let's see an application of the capacitors in condenser microphones. Here you see a condenser microphone on the right side. It is very famous. Maybe you have already used, maybe you have one at home. So what is the relation between this microphone and capacitance? Within this condenser microphone, there is a capacitor with one rigid plate and one flexible plate. Let me clean this part and let me draw, then you will better understand. Let's consider here we have one plate, and here we have another plate. Just consider that this plate is fixed, okay? It does not move. But here we have another plate of the capacitor, and it is free. You can move this one to the left or to the right. Then what about the distance between the capacitor plates? This distance can be manipulated. The area is same, okay, it is A, but we can manipulate the distance. We can increase or decrease the distance. Then remember the formula for the capacitors. Capacitance of capacitor is given with epsilon 0 A over D, right? We have this relation. So here we have a fixed plate on the right side, but on the left side we have a flexible plate or free plate. Then I can move it to the left or right, then I can manipulate D. If I can manipulate D, if I can increase or decrease D, then I can manipulate capacitance of the capacitor, right? Remember also this relation for the capacitance. Q over VAB. If I can manipulate capacitance by manipulating distance, I can also manipulate the charge here, right? So during the movement of this flexible plate, I manipulate the distance, then I manipulate the capacitance, then I manipulate the charge. Okay, then within this condenser microphones, there is this kind of mechanism, and due to this change in the charge, okay, so you send sound waves, okay, so then due to these sound waves, this flexible plate on the left side moves back and forth, okay, and it changes the capacitance, and then it changes the charge to flow to and from the capacitor. Then finally sound wave is converted to a charge flow, okay, that can be amplified and recorded digitally, okay. So this is the working principle of condenser microphones. They have this type of capacitor mechanism within the microphone. Do you have any question here? Then let me continue with the units of capacitance. From the physics 1, from the previous lectures, also the lectures during this semester, I always suggest you to be very careful with the units, okay? Here we have the SI unit of capacitance. It is farad, and the symbol is this one. And 1 farad is given with 1 coulomb per volt. How? Because capacitance is given with this formula, Q over VAB. This is given in coulomb and this is given in volt, okay? And this 1 coulomb and 1 volt can also be written in other forms. Then 1 farad can be written in this form or in this form, okay? Actually, 1 farad is a very large capacitance. I have one example related to a 1 farad capacitor. So 1 farad is very large. Here we have many commercial capacitors, and usually capacitance is measured in microfarads, okay? Look at this one, for example. Let me magnify the picture. Here, for example, we have 470 microfarad, and here we have 1000 microfarad, and here we have 2200 microfarad, okay? So commercially available, each capacitor has its own capacitance written on the outside of the capacitor, and usually they are given in microfarads because 1 farad is a huge capacitance. So let me discuss a size of a 1 farad capacitor. Just consider that the parallel plates of a 1 farad capacitor are 1 millimeter apart. Here we have one plate and another plate here. And the distance is given with 1 millimeter. And capacitance of this capacitor is 1 farad. Then what is their area? This area is asked. So you can calculate the area by using this formula, epsilon 0 A over D. Capacitance is given 1 farad and distance is given. This is constant. Then you can calculate the area, okay, by using this expression. So now we have the area. What do you see here? 1.1 times 10 to 8 meters square. This is about 10 kilometer on a side. Okay, 10 kilometer. Is it true? Yeah. So then look at the volume of such a capacitor. It is huge capacitor. And the volume of this one, if you multiply with the distance 1 millimeter, then you can calculate the volume of this capacitor. Volume is this one, okay? Then volume is calculated with this one, 1.1 times 10 to 5 meter cube, and this is equivalent to that of a cube about 50 meter on a side, okay? It is bigger than a house, okay? It is huge. So in fact, it is possible to make 1 farad capacitor a few centimeters on a side. Actually, this is very big capacitor, okay? But you would like to produce 1 farad capacitor in very small size. How it could be possible? Is it possible or not? Actually, it is possible to make 1 farad capacitors with very small dimensions, but in that case, here within the plates of the capacitor, now we have vacuum, okay? We have one plate and we have another plate and there is nothing between the plates. So we have vacuum. Then if you have vacuum, you should have huge dimensions as we have calculated here to get 1 farad. But instead of vacuum, between the plates, if you use dielectric materials, then you can produce huge capacitance with small sizes. And in the dielectric part, we will discuss this one. Any question? Let me continue with the second example, properties of a parallel plate capacitor. The plates of a parallel plate capacitor in vacuum are 5 millimeter apart and 2 meters square in area. A 10 kilovolt potential difference is applied across the capacitor. Compute the capacitance C, the charge on each plate Q, the magnitude of electric field between the plates E. Okay, these are asked. So we have plates of the capacitor. Actually, I can just solve it, okay? I know the equations and just put numbers and then you can solve it. But just try to understand the mechanism and just try to imagine how it looks, okay? It is usually very helpful. So the distance is 5 millimeter and the area is 2 square meter, and between the plates I apply 10 kilovolt. It is huge voltage. Okay, then what about the charges stored on each conductor, and what about the capacitance of this capacitor, and what about the electric field in between? Capacitance of capacitor is given with this expression A over D times epsilon 0. A is given and the distance is given. Then I can calculate the capacitance in microfarad. What about the charge? The charge on the capacitor is given with this expression. Actually, always remember this formula, okay? And if you take charge from this relation, then we have calculated the capacitance and we know the potential difference between the plates. This is 10 kilovolt. It is given in the question. Then you can calculate the charge on each plate of the capacitor. It is 35.4 microcoulomb. And we have 2 plates of the capacitor. Okay, so here we have positive Q charge and here we have same amount of negative Q charge. So Here we have found the magnitude. Then on the positive side, we have discharge. On the negative plate, we have discharge. And what about the electric field? In the previous chapters, in chapter 21, in chapter 22, we have calculated electric field of this metal plate, for example, electric field on the surface of this plate. Remember your old information. It is given with sigma over epsilon 0. What was sigma? Sigma is surface charge density, okay? And this sigma is also given with Q over A. Remember, we have also learned rho, volume charge density, and we have learned lambda, linear charge density. Okay, here, since we have plate, then we have sigma, then electric field is given with this relation, okay? And instead of sigma, you can use Q over area, this relation, because surface charge density is given with Q over area. Then we know the Q, we know the area, we know the epsilon 0, and we can calculate electric field magnitude. It is given with 2 times 10 to 6 Newton per coulomb. Another way to calculate the electric field, remember 2 parallel plates and the electric field in between. If you know the voltage difference in between, and if you know the distance between the plates, you can also calculate electric field in this form. This is the voltage difference between the plates, and this is the distance between the plates. Then you can calculate electric field. Actually, we know VAB. This is 10 kilovolt. It is given in the question. And distance between the plates is also given. Then you can calculate electric field. It is done here in the evaluation part. And what do you see here? You can get the same result. You see? Any question? Let me continue with spherical capacitor. Here in this picture, we have a spherical capacitor. 2 concentric spherical conducting shells are separated by vacuum. The inner shell has total charge positive Q and outer radius are A. Just consider here we have one shell, inner shell, and we have an outer shell, okay? And it has positive Q charge and this has negative Q charge, and there is certain d distance between them, and this sphere has certain RA and this outer shell has certain RB. Okay, it is given here. Then find the capacitance of this spherical capacitor. So capacitance is asked. In order to calculate the capacitance, I need to know the charge. Then I need to know the potential difference between A and B, between these spheres. If I know the potential difference, then I can calculate the capacitance. What I have told you at the beginning of this lecture, the electric potential, which you have learned during the last chapter, is very important in order to calculate the capacitance of capacitor in this chapter, okay? If you learned electric potential calculations very well, then within this chapter, in the capacitors, you can be very strong, okay? You can solve questions. For example, here, capacitance of the spherical capacitor is asked. Then, if I know the charge, if I know the potential difference, then I can easily calculate. So, how to calculate the potential difference between these two spheres? This is the topic of the previous chapter, okay? Then, this is the potential difference at A point, and this is the potential difference at B point, let's say. And if you calculate them with this relation they are given and put them here, then you can calculate the potential difference between the spheres. Okay, if I know the VAB, others are very easy. Just use this expression and put VAB here, then you can calculate the capacitance. And if numbers are given, for example, RA is given 9.5, it is not given in the example, but here, if you have this relation, and if you know the radius of the spheres, then you can easily calculate the capacitance. It is given with 110 picofarad. Any question here? As I told you, I am repeating this information. Please carefully repeat the electric potential part. If you understand the electric potential part, it will be very helpful here also within the capacitors. Okay, because you have to use potential difference in the formula of the capacitance of capacitor. Okay, let me finish these examples with this cylindrical capacitor. Here we have two long coaxial cylindrical conductors. One cylindrical conductor is this one, and another cylindrical conductor is this one. And they are separated by vacuum, okay? There is nothing between the conductors. The inner cylinder has radius RA and linear charge density positive lambda. And the outer cylinder has inner radius RB and linear charge density negative lambda. Find the capacitance per unit length for this capacitor. So what is asked? Capacitance per unit length. What is this? So in order to calculate the capacitance, you need Q over VAB, right? If you know the Q, if you know the VAB, then you can calculate the capacitance. How to calculate Q? Lambda is given with Q over L, right? This is linear charge density. And if you take Q from this expression, you can write lambda times L. Just put it there. And what about the VAB, potential difference for this cylinder? We have done it during the last lecture, okay, in example 23.10, okay? So if you know the potential difference and just use this one, then you can calculate the capacitance of this capacitor, okay? So this is the capacitance of the capacitor, this is the length of the cylinder, and these are the RB and RA radius of the cylinders. And then in the question, the capacitance per unit length is asked. Okay, so you have calculated capacitance and divide by the length, then this is the result. And what we have here, we have 2 pi epsilon 0. If you know the epsilon 0 is given with this one, 8.85 picofarad per meter. Put it there. And if you know the radius of the cylinders, then you can calculate this one. Okay, so I am repeating, in capacitance of capacitors, charge is important and potential difference in between is important. And if you know this potential difference between the plates, then you can easily calculate the capacitance. And this is given in the previous chapter, okay? If you understand the electric potential part of this semester, and then you can easily calculate capacitance within this chapter. I hope it is clear. Any question? Then let me continue with the capacitors in series and parallel. Actually, in the market, you can find many different capacitors with different sizes, with different shapes, and with different capacitance values. Okay, so they have some certain standard capacitances and working voltages. But in applications, you may need your own capacitance for a particular application. Then you need final capacitance and final working voltage. Okay, then what to do? Then in this case, you can combine capacitors in a series or parallel connection. So we will do that now. Capacitors in series. Here we have capacitor 1. We have two plates. One is positively charged, the other one is negatively charged with the same amount of charge. And here we have another capacitor, capacitor 2. So we have same Q charge here, positive charge, and here we have same negative charge. And we have potential difference between these terminals, okay, VAB. Just consider here we have battery, something else. And what about the equivalent capacitance of these two capacitors? So since they are connected in series, I can write this expression. VAB between A and B, okay, potential difference, is equal to VAC between A and C. Here we have VAC V1 plus VCB between C and B. Here we have another potential difference. Okay, so the total potential difference VAB is given with V1 plus V2. VAB is equal to V1 plus V2. Remember the formula. C is equal to Q over V or VAB, okay? Then from this one, I can get this relation Q over C, right? So instead of V1, you can use this one. Instead of V2, you can use this one. Then here, just use them. Instead of V1, Q over C1. Instead of V2, Q over C2. And what is VAB? VAB is given with Q over C equivalent. And here we have Q over C1 plus Q over C2. Then finally, if you cancel this Q values, then we will have this one. 1 over C equivalent is equal to 1 over C1 plus 1 over C2. And this is valid for capacitors connected in series. And the important thing here is that the equivalent capacitance, the result is less than individual capacitances. And if you have many capacitors connected in series, you can also write the total potential difference across the series combination with this expression, and equivalent capacitance of series combination can be written in this form. Any question here? Then what about application? Actually, capacitors are used everywhere, and also the series combination and parallel combination of capacitors are also used everywhere in applications. Here you see touch screens. The touch screen on a mobile phone or on an MP3 player, or as shown here on the right side, you may also seen in some movies, okay? A medical device uses the physics of capacitors. Behind the screen are two parallel layers. Here you see a screen, and there are two parallel layers, one behind the other, of thin strips of a transparent conductor such as indium tin oxide. This material is very important. It is also used in solar panels. A voltage is maintained between the two layers. The strips in one layer are oriented perpendicular to those in the other layer. So just consider that we have strips like this in one layer, and in another layer we have strips like this, okay? And the points where two strips overlap act as a grid of capacitors. When you bring your finger, a conductor, okay, your finger here, and then the front conducting layer act like a second capacitor in series at that point. We are talking about capacitors in series, okay? And when you touch here, the front conducting layer act like a second capacitor in series at that point. Then the circuitry attached to the conducting layers detects the location of the capacitance change. Actually, this point has certain capacitance, but when you put your finger on this point, you change the capacitance. Now you have different equivalent capacitance, okay? Then the circuitry detects this one, and then so detects where you touch the screen. This is the working principle of touch screens, and seriously connected capacitors explain the working principle of this type of screens. Now let me continue with the capacitors in parallel. As you see here in this picture, here we have one capacitor with Q1 charge, and here we have another capacitor with Q2 charge. Okay, this side is positive, this side is negative. This side is positive, this side is negative. And between this A and B, we have potential difference VAB. And what about the equivalent capacitance of this parallel connected capacitors? So this has C1 and Q1, and this has C2 and Q2. What about the voltage here? Since they are connected in parallel, the potential here V1 and potential here V2 are equal to each other, okay? And V1 is equal to V, V2 is equal to V, and V is equal to VAB. I think everything is clear. Then remember the formula. C1 can be written in this form, Q1 over V. C2 can be written Q2 over V. Okay, then if you take Q1 and Q2, you can get these expressions in terms of capacitance and potential. Then the total charge is the sum of the individual charges. Here we have two charges, okay, on the capacitors, and the total charge is given with Q1 plus Q2, and the equivalent capacitance is given with this expression, C1 plus C2 in parallel connected capacitors. Any question here? Okay, if you have more than two capacitors, if you have three capacitors or four capacitors, then the total charge of the system, okay, in parallel combination is given with the sum of the charges of each capacitor, and the equivalent capacitance, again in parallel combination, is given with the capacitances of individual capacitors. So this was the parallel and series combination of capacitors. Here I have few examples, then I will continue with the energy storage in capacitors. Let me finish these two examples and then we can have a break. Capacitors in series and in parallel. In figures 24.A and 24.9, we are talking about this one. This is the 24.8 and this is the 24.9. Okay, these figures in the book. What do you see here? We have a series combination of the capacitors, and here we have parallel combination of the capacitors. And C1 and C2 are given 6 microfarad and 3 microfarad. And the potential difference between A and B is also given, VAB 18 volt. Find the equivalent capacitance and the charge and the potential difference for each capacitor when the capacitors are connected in series and in parallel. In case of series combination, equivalent capacitance is given with this one. I know C1 and C2, then I can calculate equivalent capacitance with 2 microfarad. And we know that C is given with Q over V. Then if you take Q from this expression, then you can get this one. Then you can get the charge on each capacitor in series. It is given with this one, 36 microcoulomb. And what about the potential difference V1 and potential difference V2 for each capacitors? Again, by using this relation, okay, you can calculate V1 and V2, Q over C1, Q over C1. We have calculated Q. In series connection, here we have same Q charges on the capacitors. Don't forget this one. It is very helpful information. And in part B, we will do the same for a parallel combination of the capacitors. And in this case, equivalent capacitance is given with this expression. It is given with 9 microfarad. And Q1 is given with C1 times V. Now we have same potential, okay, for the capacitors, but we have different Q charges. Okay, in case of series connection, we have different potentials, but we have same Q charges. Don't forget this one. Then you can calculate Q1 and Q2. Let me finish with this example, a capacitor network. Find the equivalent capacitance of 5 capacitor network shown in this figure. Here we have one capacitor with 3 microfarad, another capacitor 11 microfarad, another capacitor 9 microfarad, another capacitor 12 here, and 6 microfarad here. So what is the final equivalent capacitance? So in order to calculate this one, first of all, you can calculate here 2 capacitors connected in series. Then you can find this one here, equivalent capacitance. And then here we have 1, 2, 3 capacitors connected in parallel. Then you can calculate this capacitance. And now here we have 1 capacitance and another one. They are connected in series. Then finally you can calculate the equivalent capacitance of this 5 capacitor network. I hope it is clear. Let me continue with the energy storage in capacitors. As we have discussed at the beginning of this lecture, we can store energy in capacitors, and it has many applications in daily life in the industry. But how to store energy in capacitors? Just consider that we have parallel plate capacitor. Let's say this side is negative and this side is positive. And how to store charges on this capacitor? In order to store charges on this capacitor, we have to do a work, okay? And this work is given with this expression, VAB. In order to store this charge, okay, you have to do this work. We have learned this one during the last lecture. Or you can also write this one in this form. Okay. So in order to store charges on the plates of this capacitor, we have to do work. Okay. And after this work, we store this energy in the capacitor, okay? So then later on we can use this energy stored in the capacitor. So how to calculate this energy? Today we will do that. When the capacitor is completely filled and when it reaches to its final Q charge, let's say here we have positive Q charge, here we have negative Q charge, then the potential difference between the plates is given with V, okay? Then we have this one. This is the capacitance of the capacitor. This is the final charge, and this is the potential difference between the plates. Just consider that for some time we store this small Q charge on the plates, okay? This Q is smaller than capital Q. And in this case, the potential difference between the plates, let's say, is given with Q over C. This is the final potential difference when we store the maximum Q charge on the plates. And this is the intermediate potential difference between the plates when we store certain Q charge, okay, on the plates. And at this stage, the work dW required to transfer an additional element of charge dQ. So just consider that at the beginning, the charge is Q, and we would like to add another dQ charge. And in order to add this dQ charge, we have to have this work, dW, okay? And dW is given with V times dQ. Work is given with Q times V. We have learned during the last lectures, okay? And in order to have this infinitesimal work, then we have this potential difference between the plates, and here we have infinitesimal increase in the charge of the plates, okay? Then instead of this V, just use this expression. Okay, V is given with Q over C, and here we have dQ, Q over C, dQ. This is the work required to transfer an additional element of dQ charge. Okay, then at the beginning, if there is no charge, the work is 0, okay? And in the maximum case, if we totally charge the capacitors with Q charge, then the work will be maximum. And then just integrate from 0 to maximum work, and dV here we have, and just use this dV equation, Q dq over C, and charge will increase from 0 to Q. We have plates. At the beginning, we have 0 charge on the plates, and finally charge will increase up to Q. Okay, so this is the charge of the capacitors at certain time, and we would like to increase their charges with dq. Okay, and if you solve this integral from 0 to Q, then you can get this expression. This is work to charge a capacitor, and this is also equal to the potential energy stored in the capacitor. Okay, we have to do this work to store this Q charge on the capacitors, on the plates of the capacitor, and it means that we stored this energy between the plates of the capacitor. Okay, so if we define the potential energy of an uncharged capacitor to be 0, just consider at the beginning potential energy of the capacitor is 0 because charge is 0. Okay, then omega work is equal to the potential energy of the charged capacitor. So after certain time, we totally charge the capacitor, and then in order to charge the capacitor, we have done this work, and then this work is equal to the potential energy stored in the capacitor. Then the potential energy stored in the capacitor is given with this expression, Q square over 2C. This one. Or you can write this one like this. Remember this relation, Q over V, and here instead of C or instead of Q, you can, for example, instead of Q, you can use this one, C times V. Just use this one, take its square, and then you can get this relation. Or you can also write the potential energy in this form, 1/2 Q times V. Okay, they are all same. And what about the unit of the potential energy? We know that it is given in joule because it is energy, right? And here we have Q, it is charge in clumps. And here we have C, capacitance. We have learned in the previous part of this lecture, it is given in farad, or coulombs per volt, okay? And here, other forms of the equation for the potential energy, but each of them gives us joule, okay? This is the unit of the potential energy. I hope this part is clear. If not, please let me know. Then what about the application? We have already discussed at the beginning of this lecture that the flashlights or electronic flash units in the mobile phones use capacitors, okay? And the energy stored in the capacitor, and it is released when the button is pressed to take a photograph. Or here you see many capacitors on this circuit board. You see many different capacitors, okay? So they are used to stabilize the voltage on this board. Very important in applications. So you store energy, and the energy stored in the capacitors is released very slowly, okay? Then you can stabilize the voltage on this board, and then you can preserve the other electronics used in this circuit board. And here there is another application. This is the Z machine. You can check in internet, okay, Z machine. It uses a large number of capacitors in parallel to give tremendous equivalent capacitance. Remember the parallel combination of the capacitors. Equivalent capacitance is given with C1 plus C2 plus C3, and it goes, okay? Here, there are many capacitors in the Z machine. They are connected in parallel, okay? And finally, there is a huge equivalent capacitance of the system, and the potential energy can be stored in this machine, okay, with even a modest potential difference V. The arcs here you see many arcs. You see, okay, bright lights, let's say. The arcs shown here are produced when the capacitors discharge their energy into a target. And this heats the target to a temperature higher than 2 times 10 to 9 Kelvin. So within the capacitors, we can store the energy, and we use this energy for different applications. Okay, this is the energy storage in capacitors. And let me finish this part with the electric field energy, how to store electric field in the capacitors, and what is the relation between the electric energy density and electric field in the capacitors. We have a term, the energy per unit volume. The energy per unit volume with the small u, okay? It is also called as energy density, okay? Energy density. What is it? This is the energy per volume. So in the previous part, we have found that energy is given with, potential energy stored in the capacitor is given with this expression. And what about the volume of a capacitor? Here we have one plate, another plate, okay? And each has A area, distance is D, and the volume of this capacitor is given with A times D. Just use this volume here, A times D. Then energy density or energy per unit volume in a capacitor is given with this expression. Here we have C, here we have V. We have learned this one in the previous lectures, and just use this V here instead of V square, and instead of C, just use this expression. Then finally, electric energy density in a vacuum or energy per unit volume is given with 1/2 epsilon 0 E square. This is the magnitude of electric field between the plates, and this is the electric constant, and this is the electric energy density in a vacuum. I hope this part is clear. If not, please let me know. Let me continue with example 27.7 from the book, Transferring Charge and Energy Between Capacitors. We connect a capacitor C1 8 microfarad to a power supply. Here we have a capacitor, and we connect this one to a power supply and charge it to a potential difference V0 120 volt, and disconnect the power supply. Okay, then the potential difference is 120 volt between the plates of the capacitor, and capacitance of the capacitor is given. Then we can calculate the charge stored on the capacitor. We can also calculate the energy stored in the capacitor. And what about the question? Here there is a switch, and on the right side we have another capacitor with 4 microfarad. Switch is open at the beginning. What is the charge Q0 on capacitor 1? What is the energy stored in capacitor 1? Capacitor 2 is initially uncharged. It is empty. Q is 0 here at the beginning, okay? We close switch S. After charge no longer flows. What is the potential difference across each capacitor? And what is the charge on each capacitor? What is the final energy of the system? So here at the beginning we have a capacitor. It is empty. And then we use a battery. Okay. These are the battery terminals. And then I connect these terminals to the capacitor and I charge this capacitor to certain value, and then we have this potential difference between the capacitor plates. At the beginning, switch is opened and there is no connection between capacitor 1 and capacitor 2. So after completely charging the capacitor 1, we close the switch, okay? Then charges from this side goes to this side, and this charges goes from this side to the capacitor 2, okay? So after charge no longer flows, what is the potential difference across each capacitor? So what will be the potential difference here? At the beginning it was 120 volt, but what will happen in the final situation, and what will be the potential difference here, okay? And what is the charge on each capacitor? Here at the beginning it is Q0. What is Q1 in final condition? What is Q2 in final condition? And what is the final energy of the system? This is the question. Let's start with the initial charge of the capacitor 1. At the beginning, initial charge is 0. Then we use a power supply and charge it to a potential difference V0. So we have capacitance 8 microfarad and we have the final electric potential of the capacitor. Then we can calculate the charge of the capacitor after charging it with a battery. Okay. And what about the potential energy stored in the capacitor? By using 1/2 Q0 V0, I can calculate the potential energy. You can also use this formula or this formula in order to calculate the potential energy stored in a capacitor. Then, when we close the switch, the positive Q0 charge is distributed over the upper plates of both capacitors, and negative charge minus Q0 is distributed over the lower plates. Okay. Let Q1 and Q2 be magnitudes of the final charges on the capacitors. This will be final charge on the capacitor 1. This will be final charge on the capacitor 2 after closing this switch. Okay. And then this Q0 charge will be shared by Q1 and Q2. Okay. And then Q1 is given with this expression. Always keep this formula in your mind. Okay. Then Q2 is given in this expression. And what about the equivalent capacitance? It is also given with C1 plus C2, okay, for the parallel case. And then we have this one. This is the total charge of the system. This is the equivalent capacitance of the two parallel connected capacitors. And now we have 80 volt. Okay, since they are connected in parallel, 80 volt is here and 80 volt is here. And we know Q1 is this one, Q2 is this one. Then the final energy of the system can be calculated with this form. So what do you see here? The final energy is 0.038 joule. And at the beginning, the initial potential energy stored in the capacitor is given with 0.058 joule. So what do you see here? the final potential energy stored in the capacitors is smaller than the initial potential energy stored in this first capacitor. Why? Because the difference was converted to energy of some other form. The conductors become a little warmer because of their resistance, and some energy is radiated as electromagnetic waves, okay? So some part of the energy is lost in other forms. Do you have any question here? Let me continue with the electric field energy, example 24.8 from the book. What is the magnitude of the electric field required to store 1 joule of electric potential energy in a volume of 1 cubic meter in vacuum? If the field magnitude is 10 times larger than that, how much energy is stored per cubic meter? So we know that energy per unit volume or energy density is given with this expression. You see, 1/2 epsilon 0 E square. What is this? This is energy per unit volume, okay? And if you know this one, you can calculate the magnitude of the electric field. So here we have electric field. It is given with this form of the equation, okay? You can get this electric field from this expression in this form, 2U over epsilon 0, and U is given, okay, 1 joule per cubic meter. It is the volume, and electric potential energy is given, okay? Then U is given, just put it there. Epsilon 0 is constant, put it there. Finally, you can find the electric field in Newton per coulomb or in volt per meter. Both are the units of the electric fields used in the SI system. And the part B, if the electric field magnitude is 10 times larger than that, how much energy is stored per cubic meter? So just look at the equation, 1/2 epsilon 0 E square. So if electric field is 10 times larger, then when you take the square of 10, then the potential energy increases by a factor of 10 to power 2 or by a factor of 100. So the energy density becomes 100 joule per cubic meter. At the beginning, it was 1 joule per cubic meter. And if you increase the electric field 10 times larger than the beginning, okay, then energy density will be 100 joule per cubic meter in the final case. Let me finish this part of my lecture, this last example. 2 ways to calculate energy stored in a capacitor. The spherical capacitor described in example 24.3, we have discussed this example, has charges positive Q and negative Q on its inner and outer conductors. Find the electric potential energy stored in the capacitor. U is asked, and by using the capacitance found in example 24.3 and by integrating electric field energy density U. So, electric potential energy stored in the capacitor is asked, but you can calculate this U in 2 ways. One is by using this formula. U is given with 1/2 Q square over C, okay? And if you know the capacitance, if you know the Q, you can calculate this one. Or by using this formula, if you know the electric field, you can calculate this energy density, and by using the energy density, you can calculate the electric potential energy stored in the capacitor. So in both cases, you will get the same result. So in example 24.3, we have calculated the capacitance of a spherical capacitor, this one, remember, and then just put this C here in this equation. Then you can calculate the electric potential energy stored in a spherical capacitor, or by using this formula, 1/2 epsilon 0 E square. E, we know E, okay? This is the electric field in the region between the two conducting spheres. It has this magnitude. Here you have to use your old information, previous information from chapter 21, chapter 22, and chapter 23. Then just put this electric field here. Then you can calculate energy density. And from the energy density, you can calculate the electric potential energy, because this U is given with U over unit volume, okay? Or if you take this U from this expression, you can get this relation, this one, okay? Then U is known, just take this one, put it there. And what about the volume? Area times dr, this is the volume of the sphere. Then if you solve this integral, finally you can find the electric potential energy stored in a spherical capacitor. And what you see here, that the results are same, but this calculation is much easier, okay? Okay, with this one, I finished this lecture. And next lecture, we will continue with the dielectrics, and we will use dielectrics between the plates of the capacitors. Here, within this part of my lecture, we have discussed the capacitors with the plates, and between the plates, we have nothing, just vacuum, okay? But generally, we use dielectric materials between the plates, okay? And then you can increase the capacitance of the capacitor, and you can store more energy. So in the next lecture, we will continue with the dielectrics. Take care of yourself. Bye-bye.